Alright, so this is the lecture for homework 1. So we'll get to, let's get to that section. Alright, so hopefully you've already looked at these two intros. Alright, so here's week 1. And so here we are right here. And this is of course homework 1. This is of course due Sunday by 10 p.m. and there's another homework that's going to be due. So what I'm going to do is open up this PowerPoint chapter 2. So we're going to start with chapter 2. I'll talk about metric prefixes as well. Let's see, I have that open already. Where is it? Let's see. Where's my PowerPoint? Here we go. Alright, so this is chapter 2. It's all about motion. The study of motion is generally called classical mechanics. At least the what we're doing in chapter 2 is classical mechanics. It's the mechanics that Isaac Newton taught us. So alright, let's move on. One of the first things that we encounter in classical mechanics, or the study of motion, is that there's a net force that's required to change the state of motion, and there's actually a really good formula for that. Let me show you that real quick. This will allow me to show you. And so what that is, it looks like this. In formula form, it says that the force on an object is equal to the mass of the object times a quantity called the acceleration. Let's make that's an A. Okay. And since this is our first formula, I just want to point out a couple of things. With all the formula that we're going to have throughout the semester, you always have to use proper units. And anytime I write a new formula, I'll always include the units, or talk about the proper units. So, and we usually use standard international units, not all the time, but usually. So the units for force are called newtons. And instead of pounds, for example, that's the English units. The units for mass are kilograms. So that's a kilogram, of course, is 1,000 grams. Kilo, the metric prefix K, kilo, there means 1,000. We'll talk about that a little bit later. And the units for acceleration are meters. These are kind of strange units. Meters per second, or another way of writing that, of course, is meters per second squared. All right, and those are the proper units. Now, if you're given a quantity that's not in those units, we have to convert. And of course, that the conversion from one type of unit to another is really the subject of chapter 1, which is covered in chapter challenge 1 and chapter challenge 2. So I'll leave those. There's already examples there for those. All right, so let's get back to this idea of force. All right, so back to the PowerPoint. There's descriptions of motion which really have to do with Galileo, and then the explanation of motion, which is involving force, which is Isaac Newton, who lived about a generation after Galileo. Anyhow, so the basic idea about motion starts with the concept of position, the idea of speed and velocity, which are actually two different quantities. We'll talk. They're related, of course, but speed, I might as well say it right now, is that speed is what we would call a scalar quantity, a quantity that only requires magnitude. Velocity is what we would call a vector quantity in physics, and so velocity requires not only magnitude but also direction. And there's a lot of quantities that are like that in physics. For example, force is a vector quantity. It requires magnitude and direction. Acceleration is another quantity that is also a vector quantity. It requires magnitude and direction. And acceleration, of course, is the quantity that we just mentioned in the formula, which, by the way, that F equals ma, I don't know if I said that, is called Newton's second law of motion. So we'll get back to that shortly. We're going to look at horizontal motion, like on a ball rolling on a flat table, objects that are falling or rising. If you throw an object straight up, it undergoes what we call free fall, and so that's also considered, even though it's rising, that object is considered a falling object, or at least the equations that describe it work just as well, whether the object's going up or falling or coming down. And then we'll talk a little bit about compound two-dimensional motion. Okay, so that is if an object is moving horizontally and it's falling at the same time, like like if you hit a ball horizontally off a cliff, and the object would fall as well. All right, so let's move on. For Isaac Newton, there's this idea of forces that are the causes of motion, or the causes of changes in motion. He also uses this idea of inertia. Inertia is the resistance an object has to changing its motion. It turns out that this idea of inertia and the concept of mass are basically the same thing. The more massive an object is, the greater its inertia. And then we'll talk about Newton's three laws of motion. We've already talked about the second law very briefly. We'll consider momentum. We're not covering everything. I won't get into circular motion. I'll very briefly talk about Newton's law of gravitation, and yeah, we don't have time to do everything. So, all right. So measuring motion, of course, there are two fundamental components. Those are, of course, distance and time. All right. So distance we measure as changes in position, and of course changes in time. And change is the final quantity minus the initial quantity. All right, I was just mentioning change, and so the symbol that we generally use for change is a delta symbol. So there's delta, so that means change. Okay, that didn't exactly come out, sorry. Change. Okay, so you can have any quantity change, of course. What we were talking about with the general concept of motion is a change in position, so we'll call that, for example, delta d, where d is the distance. And so what change generally means is the final quantity minus the initial quantity. So what we'll talk about is d final. The subscript here just means final, minus d initial. Okay, so the initial quantity. And the same thing goes with time. Delta t is going to be t final minus t t initial. Alright, so going back to the PowerPoint presentation, here, let's make that larger. Alright, so measuring motion, and we just covered this. Okay, so changes in position over changes in time. Here's an example from on the PowerPoint. They're showing different times, different positions, and what we do is we talk about the speed, which is of course the position, the change in position divided by the change in time. Well, I'll show you the examples of each of those. Remember, speed is just the magnitude, the size of it. For example, 5 meters per second. That would be the speed. The velocity would be 5 meters per second to the left or to the north or something like that. Something that includes direction, however you want to consider direction. Now, in this class, we're just going to talk about direction either to the right or to the left, or up or down. So those are, we're just going to really be talking about two-dimensional motion. And then there's another quantity, which is really the change in velocity, is what's called acceleration. Okay, so the change in velocity, and it's the same idea. So the acceleration is all right. So let's talk about what acceleration is. I'll define it using our concept of change. So acceleration is the change in velocity divided by the change in time. All right, and also velocity, it turns out, which I guess I should have covered already, but velocity is, this is something separate here, the velocity of a quantity is the change in position divided by the change in time. Okay, so that quantity, this quantity here, can change with time, and that's what we mean by acceleration. All right, so let's go back to our PowerPoint. All right, so oops, all right, so we already covered this. So here it is. Again, this is just in words. It's really the change in distance divided by the change in time. That's the speed. The average speed is really what you measure. For example, on an overall trip, if you take a really long trip, you're starting, you're stopping. Let's say you're turning, you're changing speeds. The average speed is the total distance divided by the total time. And there's some examples, some questions about this in the homework, and I'll try to do an example or two. Now, what's this quantity called the instantaneous speed? Now, that is a quantity where this time down here, this time interval, the change in the time, starts to get really, really small. And that's actually, the instantaneous speed is, for example, what you would read on a car speedometer. That's telling you exactly how fast you're going at any instant in time. Okay, and all right, so let's see what the next thing is. So it says, calculate the average speed between the trip times of 1 hour and 3 hours. So the total time is 2 hours. The total distance here, this is the final, would be 150 kilometers minus the starting position. You don't always start at 0, for example. So let's say the starting position was 50 kilometers. 150 minus 50 would be 100, and then divided by the total time, which is 2 hours. I mean, that you can actually just do in your head. 100 divided by 2 is 50, so it would be 50, and the units here are kilometers per hour. sometimes we'll use that. Okay, so, and this is another way of writing average. It's like a V